In my previous video on permittivity, we learned that it qualitatively represents the resistance to the formation of electric field in the medium. Suppose we take a medium here, and if I apply an external electric field, then there will be a reduction in the net electric field inside the medium. This reduction is due to the resistance from the medium to the electric field formation. And this is quantified as the permittivity. If we take a vacuum medium, so vacuum means no charges or dipoles in the medium, it's totally empty, the permittivity is not zero. That means if the permittivity is not zero, that means it is behaving like a medium or a dielectric medium. So now the question is, if a vacuum is truly empty, why does it have a permittivity at all? Should not the absolute permittivity be zero? This is what we are going to discuss in this video. First, let us define vacuum from classical and quantum mechanics point of view. Now, in classical physics, vacuum is something which is empty. It does not have particles or fields. So the energy is zero and it's a static environment. But from quantum mechanics point of view, the definition of vacuum is different. To understand this, let us recall the uncertainty principle in terms of position and momentum. Here delta x, it represents the uncertainty in position, or we can say it's a quantum fluctuation of position. And x and p here, they are known as conjugate pairs. Now, in quantum field theory, electric field and magnetic field they can be represented as field operators. So corresponding to electric field, we can write the uncertainty principle. Here A is the conjugate pair of electric field. Now, if you see this relation, the fluctuation in electric field cannot be zero. If it is zero, then the fluctuation in A will tend to infinity, which is not possible. So, quantum mechanics says that in vacuum, where there is nothing present, there is always a non-zero fluctuation of electric field at its ground state. Now, if I compare these two definitions, classical vacuum, it's static, but quantum vacuum, this is not static, it's a dynamic, where the non-zero fluctuation of electric field is happening in the medium. To understand the fluctuation that is happening in the vacuum, we need some concepts from quantum field theory. This topic is very vast, but here we'll take a simple example and try to understand some basic concepts. Now, if you have two electrons, according to classical electrodynamics, there will be a repulsive force between these two electrons. And this is because the static electric field spreads out from one electron and it acts on the other electron that leads to the repulsive force. Now, in quantum field theory, forces are mediated by fields. Or in other words, instead of the forces acting directly between these particles, they are described as the exchange of force-carrying particles. Now, if we take the same example, one of the electron will emit a virtual photon and that virtual photon will be absorbed by the other electron. Now, this exchange gives the repulsive force. Now, why we are calling this as a virtual photon? Because this photon, it's not a real photon, means we cannot detect this photon. And energy and momentum conservation is guaranteed for the whole interaction, not for this particular virtual step. Now, we can represent this interaction using the Feynman diagram. So, we have two electrons and one of the electron emits a photon, virtual photon, and it is absorbed by the other electron, and the final product is two electrons. We already know that due to uncertainty principle, there will be non-zero energy fluctuation in the medium. Now, because of this non-zero energy, virtual photons they will create a pair of electron and positron. Now this virtual pair will again annihilate to form a virtual photon. Now the pair of particles which is created in this process, it's like a virtual dipole. We'll talk about this later. Now this reaction can be represented using the Feynman diagram. So you have a virtual photon that creates a pair of virtual electron and positron, and this pair again annihilates to form a virtual photon. So in vacuum, there is a spontaneous and random creation and annihilation of virtual particles, and this is what we refer to as a vacuum fluctuation. Now, what does this fluctuation look like in vacuum? To have an analogy, let us take a simple example. Suppose you have a beaker and there is a liquid inside, and let's say the liquid is static. But if you zoom in carefully, then you will be seeing some small ripples that are created and again faded with time. And a similar analogy, we can take it to vacuum medium. So in vacuum, there will be quantum fluctuation, and it's like a constantly jittering sea of temporary energy spike. Now, what will happen to this vacuum fluctuation when we introduce an external electric field? Suppose you take a vacuum here, there will be a vacuum fluctuation where virtual particles or virtual pairs are created and annihilated at different space and time randomly. Now, if I introduce an external electric field, now these virtual pairs, they are like a virtual dipole. So this virtual dipole will try to align for a short period of time with the external electric field, and this will lead to a virtual polarization. So in the vacuum medium, we are getting a virtual polarization, and because of this virtual polarization, the external field will be distorted when it enters the vacuum medium. That means this vacuum medium is behaving like a medium, and this behavior is quantified as the permittivity of the vacuum. This is why the permittivity of the vacuum is non-zero. Now, the last question here is, the vacuum is behaving like a medium. So that is why we are getting a non-zero permittivity. Then, if it is behaving like a medium, why the vacuum susceptibility is zero? Because in one of my previous video, we learned that susceptibility is the tendency to get polarized. Now, we know this relation that the polarization vector is proportional to the external electric field if the medium is linear. So, in vacuum, the virtual dipole is not a real dipole, because the virtual dipole, they are real in terms of effect, but they are not in terms of existence. And even though there is a virtual polarization, the average polarization over reasonable time scale will always be zero. So polarization is zero, that is why the susceptibility is zero. So this is the reason why vacuum has non-zero permittivity but zero susceptibility. Thank you everyone for watching this video.